forward to
Did
this.
you say the regular expression was worth 10 or 15 points?
15.
Okay, thanks.
So, let's see. So there's but that's so those assignments are they're not too tough. But again, it's a bit foreign. It can be a bit foreign the first time around to be using an external library. So I figured today that I will use that I'll be going over some practice exam for you. So let me go to my GitHub page and pull up my study guide. Okay. Classroom. Okay. Hi, Happy Feet. 1 second. Structures, study guide.pdf. Okay, and now I'll click on, I think. So I've got a couple links. One of them is dead, but this one is not. I like this one a whole lot. Practice final exam. So I figured that you might find it more beneficial, since the final is a greater proportion of your grade, for me to give you as much review as possible. Because I like a lot of these questions. Now, some of these final exams I've linked, they have stuff that you'll naturally be unfamiliar with, like balanced binary search trees that we don't cover just simply because of the time constraints. But most of the stuff we do, I think balanced binary search trees are basically the only thing we don't really cover. Again, time constraints. All right, so let's go ahead. Suppose items A, B, C, D, and E are pushed in that order onto a stack. If two items are then removed, so A, B, C, D, and E are pushed onto a stack. A, B, C, D, and E are all pushed onto a stack. The stack is then popped 4 times, and as each time it's popped up, it's put into an empty queue. So we pop it off. E, D, C, B, popped 4 times. 1, 2, 3, 4. And then if 2 items are removed from the queue, what is the next item that would be removed from the queue? And the answer is C, because we've popped, we got these off. Then we put these in, we pop them off the stack. It goes into here. Okay. If the binary search tree below is, and let me go ahead and zoom into these. If the binary search tree below is printed by a pre-order traversal, what will the result be? So pre-order means that basically we're going to do the root first, and then we're going to do our left subtree and the right subtree. So we're going to do 6 first. So that means that can't be A or B, because we always print the root first. Then we need to print out the entire left subtree in pre-order traversal, then the entire right subtree in pre-order traversal. So everything on the left needs to come before everything that happens on the right. So D is wrong, because that would be because if we look at D, that's 6, 17, 22, 9, 4, 16, 12. That's what they call level order traversal, also known as breadth first search or breadth first traversal. It's useful if you're going through a heap, but otherwise not really. It's not really what we're looking for. So 6, 9, 12. So here we're going to go ahead and do, so what's the next thing? Well, we want to do the entire left subtree, and we got to do a pre-order traversal of that. And that says next thing we do is 17. Then we do 17's left subtree, and then its right subtree. 9, and then 4. So that only matches this one. So let's keep going. then let's do 6's right subtree. 22, 16, 12. And if we look, that's what matches E. On this next question, I really like. Okay. A graph implementation that uses a two-dimensional array to store to represent the edges would be most reasonable for which of the following cases? Okay. Do we want, if we've got 1,000 nodes and 1,200 edges, 100 nodes and 4,000 edges, 1,000 nodes and 10,000 edges, 10 nodes and 20 edges, or none? So if you remember from our readings, from our lectures, there's two ways we can represent a graph, which is, as it points out, an array-based way or a linked-based way. So E is wrong because you can represent it in two ways. You can either represent it as an adjacency matrix or an adjacency list. Adjacency matrix is exactly what it sounds like, right? Which is that basically we have a matrix here and we have A, B, C, D. So we have a graph of, and A, B, C, and D are the nodes. And so adjacency matrix says, hey, I'd like, basically this is all possible. Each spot in the matrix is any possible edge in this. So a edge from B to A over here, if that's exist, we could put a 1. And if it doesn't exist, we can leave it blank or something, or put like infinity or something in there. It's not useful to put 0 a lot of the times because 0 might imply that it's a free edge. You can get from A to B for free. But the other way to do it is just basically say, hey, A has a link to B and C. Whoops. A has a link to B and C. B has a link to A, and so on and so forth, right? So that's an adjacency list. Now, the reason you use them is because some are better based on how sparse. It's all based. Which one you want to use is based off of the density of the graph, how sparse or dense the graph is. And what does that mean? It means how many of the possible edges are filled up, right? If you've got a adjacency matrix, right? You've got this big matrix over here, right? Really big with really tiny lines because there's a lot of nodes, right? Make sense? So if you've got like if you've got like 1,000 nodes and you've got one edge in the graph, right? You're wasting a ton of space because you just got a bunch of empty spaces to hold to the position of one node. Okay. On the other hand, you got yourself, again, it's like the array list, linked list thing. On the other hand, you've got if you've got a linked data structure, so if you've got a linked list, so basically I typically would use a map for this where the key is the node and the value is the list of all the nodes it's got an edge with, or the list is all the edges, right? That requires extra memory usage. That requires extra kind of overhead, right? That you don't get from a matrix. So as it gets more dense, the overhead cost becomes more, it's a linear thing, but it kind of becomes more of a fact. So the cutoff point is around 25%. Basically, if 25% of all possible edges are occupied, then you want to use an adjacency matrix, 25% or more. So in other words, and how many possible edges are there? Well, it would be the number of vertices squared. Though in a simple graph where you can have only one edge between any pair, that's the difference between a simple graph and a multigraph, right? You can only have one relationship, one edge between two nodes. If that is so, if you've got V nodes or V vertices, then number of possible pairings is V squared. So if 25% of those pairings are taken up, then you want to use the adjacency matrix. So let's go ahead and put that into practice with this. So we've got 1,000 nodes and 1,200 edges. So 1,000 nodes squared. Oh no, that's a lot of work to do, right? Oh, actually it's just 0. So no, we just double the number of zeros, right? So 1,000 nodes means there's 1,000,000 possible edges, right? There's 1,000,000 possible pairings. Here we're just using 1,200 edges. I'm going to just scratch out the zeros. This is not 25% of the possible edges, right? This is not 25%, so not very good there. Okay, what about 100 nodes? 100 nodes squared. So we've got 100 nodes, which is 10,000 possible, and then we've got 4,000 edges. So 4 out of 10, that's 40%. That's a pretty good one. I like that one. It's nice and easy to figure out, 40%. But it says most reasonable. So if there's somebody with more, that would be more reasonable. 1,000 nodes, which we already calculated, that means there's 1,000,000 possible edges. 1,000 nodes, 1,000,000 possible edges. And then we've got 10,000, and we actually have 10,000 edges. So scratch this at 4 zeros. That means 1% of all possible edges are filled. And then finally, 10 nodes at 20,000. So this one's actually easy to do math-wise because that is 10 squared is 100. 20 out of 100 is 20%. So that's almost as it's starting to get there, but it's not quite at the 25% mark. So B is our best answer here. Because it is the most most dense of all those. All right, so here we've got a binary search tree constructed of nodes that are instances of the following class. Okay. Node left, right, or sorry, val left, right. So they're using, right, so this, they didn't do generics here, whereas we spent quite a bit of time on those, right? Where if it was a generic, all we'd be doing is this, right, instead. So it's not, so we'll just keep it an integer because why not? It's no skin off our back. Okay, so consider the following method: public static node mystery, node root, blah, 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 blah. Okay, we'll go into it later. Let's finish reading the question rather than trying to analyze it, right? You consult 3 supposedly tech-savvy consultants, always a challenge there. When you get the following 3 opinions about what the method does when you pass it the root node of a binary tree, okay? Consultant 1 says it gives you the last node returned by in order traversal. 2 says it's the last node in a post order, and the last node by a level order. Okay, so again, level order, we didn't go over that in class explicitly until we got to graphs, because a level order traversal, that's just breadth first search. Okay, that's just a breadth first traversal where we do the root, then we do the root, then we do the root's children, and then we do the root's children's children. So we do the root's grandchildren and then the root's grandchildren. And so we go through each level. It's useful for iterating over a heap. We've done it implicitly, but not explicitly. All right, so which of these people actually is correct, regardless of the contents of the tree? So in other words, if we want to prove them incorrect, we just need a counter example. Okay. So let's go ahead and talk about counter examples. So the last node visited by an in-order traversal. So the last node in an in-order traversal is always the biggest thing in a list, right? So it will be the biggest thing. Okay, it returns the last node visited in a post-order traversal. What is the last node visited in a post-order traversal? What is the last thing we would print out in a level order, in a post-order traversal?
The root?
The root. visited, like technically you have to go through the root to get to the left tree. So it feels a bit weird to say you visited there, but yes, it's the root. Okay. And then finally, the level or traversal question mark. So what does this mystery do? It says, give it a root. If we don't have a right subtree, return this guy. Okay. But if we do have a else, which means, in other words, if we do have a right subtree, return calling this on the right subtree. So otherwise, we want to recurse. So then we want to recurse on this and end on this. So in other words, what we're going to do is that given a tree, we are going to go down it. We're going to go all the way to the right until we get to a node, until that doesn't have a right child, and then we're done. Make sense? So in other words, this algorithm returns the rightmost node in the tree, which in a binary search tree, in order traversal, that would be the biggest node. And the biggest node is always the right thing to the rightmost, right? Right? Because if it wasn't the biggest thing, then the thing to the right would be the biggest. So then we'd want to return that instead. So it doesn't matter how big the tree is or how we draw it, this will always return the last node. The last node visited in a post-order traversal. That's just plain wrong, because this is where, so it would work. That would be the case here. That's the only instance in which it's correct. The only instance. The minute I draw this, incorrect, because we'd want to return this guy, and we'd return the root. Sorry, and post order is the root there. Okay. Level order traversal, right? Seems like that. I mean, certainly if we draw a perfect tree, right? If we draw a perfect tree, which is almost always our instincts for drawing trees, we'd go, okay, level order traversal. We'd want to go first, and then we'd want to go 1, and then 2, 3, and then 4, 5, 6, 7, right? And so we'd want, and so we return 7. Well, let's go ahead and remove that guy, because not all trees are perfect. Okay, so the algorithm that we wrote would return that the mystery algorithm would return 3 in this case, but level order traversal would end with 6 over here. So 2 is wrong, 3 is wrong. Make sense there? So the answer is A, 1 only is correct. All right, with a poorly chosen hash function, it's possible to have a situation with the search time in a hash table of n items goes to. So in other words, it's asking how bad can we write so it's asking with a poorly chosen hash function, it's possible to have a situation in which the search time goes to what? Well, let's go ahead and write a very poorly chosen hash function and think about what happens, rather than letting our brain kind of boil over here. So I'm going to write a very bad hash function. H of k, so the hash of this key is equal to 0. That's a great hash. Sorry, that's a great, terrible hash function. Why? Because it maps everything to 0, right? So in other words, I could get equal results for hash is equal to 1 or hash is equal to 2, but hash is equal to 0 just seems much more fine, much more definite. So what's going to happen in that case? Well, the first item I put in, that's going to go fine. But the next item I put in, it's going to go, wait, there's an item already in my spot. So I got to go and resolve that collision. Okay. If we're doing open addressing, it looks kind of like this. One, Oh, I want to go into this spot. I can't. I'll go to the next spot. Oh, I can't. I'll go to the next spot. Oh, I can't. Right? And so it becomes a O of n kind of linear insertion time. On the other hand, if I'm using chaining, then what happens there? Well, I've got a slot with a linked list. So if I add our first item, get our first item, then our second item, then our third item, and it just becomes a linked list where it would take O of n time to find anything in there. So answer is A, because basically you're either doing n collisions or just turn, because everything collides with everything else, and you're either just going to have to, so you're going to have to search all n spots to find anything, which is rather inconvenient if you think about it. Hey, guess what? We did this on the practice exam, that one. Okay, let's keep going and keep it with the hash tables. Okay. A police department wants to maintain a database of up to 1,800 license plate numbers of people, so up to 1,800 license plate numbers of people who receive frequent tickets, so it can be determined very quickly whether or not the given license plate number is in database. So our task is we want to create a program that basically says they can plug in a number, and then it will say, hey, is this a frequent speeder or a frequent target of tickets? Speed of response is very important. Efficient use of memory is also important, but not as important as speed. So in other words, speed is how we decide, and space is going to be how we break ties. Which of the following data structures would be most appropriate for this task? So a sorted linked list. So looking for an item in this sorted linked list is god awful. Why? Because to find anything, you have to search for it in O of n time, even if it's sorted. Why? Well, I'm here, and this is the end. And God knows what we've got in between. But to get to the middle, I have to go n over 2. I have to do n over 2 current dot nexts to get there. And then I would have to do so I'd have to do n over 2 to get somewhere, and then possibly n plus 4, then plus n plus 8, then plus n over 16. I'm pretty sure this converges to n, right? I'm pretty sure this converges to n. So yeah, linear, regardless, it takes O of n time to find anything in here. Okay, honestly, forget about like just moving back and forth and trying to do a pseudo binary search. Just iterate through the array and save yourself some trouble, or the linked list. It will take O of n time. A sorted array with 1,800 entries. So if we've got a sorted array, okay, we've got sorted array on the other hand, getting to any specific index takes constant time. So we can do binary search on this one, right? Binary search. And doing binary search, so finding anything over here is log base 2 of n, which I'll just write down as LG of n. Computer scientists, if you haven't seen it yet, we have a special notation for our log function, which is that if we use, so right, just like if you see, just like how you can often assume log base 10, log means base 10, except in computer science. And you know that LE is going to mean log base E, the natural log. If you happen to see this log without the O, you got 2 letters, it's base 2. So it's going to be 1,800. Next, we've got 3 hash table. A hash table with, and how much space is this going to take? It's going to take constant space. So if this, by the way, if we cared about space more than we did about anything else, this would be the winner by far. But here we're looking for speed. Okay, a hash table using open addressing with 1,800 entries. Now that seems like you'd be using constant time, but you're not really, because if you've got 1,800 entries and you're going to store 1,800 numbers in there, the parking lot metaphor applies here, which is if you're trying to find an empty space in a parking lot that's almost full, right? You're looking for that one spot in this parking deck that is empty. It always takes freaking forever to find it, right? You're looking for one empty spot because you basically got to choose every possible, you got to look at every single possible spot to find it. And that's a pain. So actually this is more of a linear time than that. And you're using up just as much space now as that. Oh, address table. So a hash table using 1,300 entries. Well, now we're getting somewhere because while we're using twice the amount of space here, right? As we do entries, while half our spaces things are not going to be used. Again, the parking deck metaphor. How long does it take to find a space if that space is, if we have, how long does it take to find that space if half the spaces are empty? If half the spaces are empty in a parking deck, it's pretty quick, right? You might see a couple that have spots that are taken, but it doesn't take too long to find one, right? In fact, there's a formula we can use. It was in your textbook, and it was done by Knuth. Knuth hash table time. Speed analysis. So, let's see. Where is that formula? Yeah, I know. I'm just trying to find that formula because it is, so that is with chaining. Where am I? Why am I looking for that? Oh, right. Open addressing. Oh, there we go. Linear probing. So, yeah, really, it doesn't have that formula in here. It doesn't have Knuth's formula. Because I'm pretty sure I know it, but I don't like it doing it from memory. Wait a second, I have my textbook here. What am I doing? Ah, but it's over here. So there, that's the formula where, that's for, yep. Where it's 1 plus 1 over 1 minus the load factor. So, back to this. The load factor here is 1/2, right? Because half the spaces are taken, right? And you have n spaces, you have n items. The capacity is 2n, right? In this case, so it's 1/2, 1 plus 1 over 1 minus 1/2 for this. And I had it, I just was missing this one. because that's the average time. So so this becomes 1 over 2, which becomes 2, which means that this is 1 plus 2, which is 3. 3 divided by 2. This means it takes on average 1.5 steps to find something, constant time. Make sense? Okay. Now, the last one is hash table using open addressing with 10,000 entries. Okay, 10,000 entries. So again, look, this is going to be really quickly, but we're using, in broad terms, about 5x time, right? Moore's time. So here, let's go ahead and plug it into the formula. 1 over 1/2, 1 plus 1 over 1 minus 1/10. 1 minus 1/10 is 1. Sorry. So 1 minus 9. We're using 1/10 of the space, so to speak, because round up just makes the math a bit easier. So this becomes 9/10 on the bottom, which means that 1 over becomes 10 over 9 over here. So now we add this one, and so this would become 19. So it'd be 1/2 19 over 9. So this amount of space would be, so 1/2 of that would become 19 over 18, which calculator, 19 over 18. I said 19 over 18. 19 over 18 is 1.0, let's call it 1.05. So on average, it's going to take 1.05 lookups on average to find anything. Now, while it said speed is important, I mean, it really depends on your professor what the right answer is in this case. But I think that the difference between 1.5 and 105 is, to quote one of the answers that I got back on the exam for one of our questions, it is too small to actually care. So I would say that D is the correct answer because both of these are constant time, but D uses less memory. So that's why I would go with that one as the correct answer. All right, a Huffman tree is constructed for a text document containing 5 characters. Character E appears most frequently, then the character I is the next highest. So which of these following ones are correct? 1, 2, or 3. So
Didn't we not do Huffman trees?
I mean, I went over it in the things, but I'm not going to go over it and do it in the exam. But for reference, 1 is wrong because all the letters have to be on the leaves. And then E has to be the most common thing. And the most common thing should be at the smallest height. So 2 is the only possible correct answer. All right. An array of 7 integers is sorted for the heap sort algorithm. After initial phase of the algorithm, constructing the heap, which is the possible ordering of the array. So heap sort. So heap sort requires 2 phases, right? 2 phases. We take an array. So we take an array. And then our phase 1 of that is to heapify it. And phase 2 is to actually sort it. That is the phases for heap sort. Take an array, heapify, then sort. Make sense? And then we'll get a sorted array. I know my handwriting's terrible. Deal with it. Okay. So after the initial phase of the algorithm constructing the heap, so how do we construct a heap in heap sort? Well, what we do is we create a max heap. So the biggest item has to be the root. So D is wrong. Okay, so what we're looking over here is that, so in other words, which of the following is a possible ordering for the array? Reworded. Which of the following is a max heap? Because we're only going to accept max heaps. Make sense? If it's a max heap, then it's a possibility. All right. So 85 is bigger than its children, right? So its children, 85 is bigger than its children. And then 78 has its own children, which are these two. And it's bigger than both of these. But 45, and again, there's a formula for heaps. But 45 is smaller than its children. So this heap, the heap property has to hold throughout, right? If we write this out as a heap, 85, and this is problem, and this is letter A. We see that this violates the max heap because the smallest item in this subheap is, the biggest item isn't at the root of the subheap. The biggest, right? Not only does the biggest, so remember for heaps, it's a recursive property as well. Not only does the biggest item, so right, for it to be a max heap, that means that the biggest item in the array has to be at the top of the heap, and that your left heap and your left subheap and your right subheap, your left subtree and your right subtree both have to also be heaps. We're going to call it trees. Okay, so A is wrong. 85 is bigger than its children. So 49 is bigger than 45 and 47. 78 is bigger than these two. So 49. Yeah, this looks like a possibility. 85 is bigger than, I'm not going to answer yet because of course I could have just made a dumb mistake. 85 is bigger than both. 78 is bigger than both theirs. 49 is not bigger than those, so C is wrong. E. 85 is bigger than those. 51 is smaller than this. 51 is smaller than this, but bigger than this. It's not bigger than both its children, so E is wrong. So the answer by process of elimination and the fact we checked it has to be D. B. Yeah. Scroll up. Initial empty binary search tree shown was constructed by inserting a sequence into an initially empty tree. Did something like this on our exam, I believe. Which of the following sequences will not produce this binary search tree? So, right, 5. So if we think about, so in other words, which of these will, so let's just put them in order. 5, 3, 4, that would produce that. 9, 12. It's weird. It might seem weird until you actually go through it. 7, 8, 6, 20. This binary search tree would then be constructed by that sequence. Okay. Similarly, 5, 9, 3, 7, 6, 8, 4, 12, 20. What would not produce this? If we got a number that wasn't in it, or that we got numbers inserted in such a way that would produce a whole, and therefore the numbers would be out of order. So 5, 9, 7, 8, 6, 12. I'm on C right now. 20, 3, 4. So those are fine. We did the right subtree before. 5, 9, 7, 3, 8, 12, 6, 4, 20. And finally, 5, 9, 3, 6, 5, 9, 3, and then we'd put in 6. 6 is greater than 5. 6 is less than 9. So 6 would go here, but that's wrong, right? Because 6, should be going here. So if we were to continue, we'd get 7, then 8. So E is our answer here. Okay. Suppose the middle rows in a keyboard are inserted into succession in an initially empty binary search tree. Draw the tree after the sequence of insertion is made. A, S comes after A. So this is a very unbalanced tree that we're going to about to draw. S comes after A, D comes before S, but after A, D comes after A before S, then F. F is after, before, after. G, H, J, K, and so on and so forth. It's a very unbalanced tree, but the next question is asking you to do it with a self-balancing algorithm, 2-3 tree, which, nah. This one is worth paying attention to because I asked something pretty much like it on the exam, on the final exam. So we are given an empty hash table of size 7. Voila, like, you know, there we are, hash table 5-7. And it's going to use open addressing, right? Open addressing means we resolve any conflicts we have by looking for the next, by inserting nodes. And if there's a conflict, we have the node that we're trying to insert, look for the next available spot. Make sense? Here's the sequence that we're going to insert. Insert these keys as each of the following approaches. If the overflow occurs, say so and indicate the element that causes the overflow, which I'll just draw. And so this says, hey, here's our hash function, resolve it with linear probing and resolve it with quadratic probing, right? Linear probing, if you remember, means open addressing says look for the next available space. Linear probing says defines next as literally the next available space index-wise, whereas quadratic probing basically says I'm going to look 1 squared away from my space I'm trying to get, then 2 squared, then 3 squared, then 4 squared in order to create less clumps. Okay, so 15. So if we want to insert 15 in, so 15 mod 7. 15 mod 7, it gives us 1, so we want to put it into index 1, right? What is how did I calculate that? What is the remainder of 15 after you divide it by 7? So 7 the biggest number below 15 is 14. That's one way to think of it. So we do 15 minus 14 to get 1. Another way to do it is just keep subtracting 7 until you get a number less than 7, which would be 1. So doing modular arithmetic in your head isn't too hard. You just got for small numbers like this. For big numbers, it's annoying. Unless the big number, unless you get it in this format where y is bigger than x, in which case your answer is x, and that becomes super easy. Okay. So 15, 17, 8, 23. So let's put 15 here. Next, let's put in 17. 17 mod 7 is 3. So we put the 17 in here, right? Next, we want to put in 8. 8 mod 7 is 1, but we can't put the 1 in, so we can't put 8 in because its space is already taken. So we look for the next available space, which is 8. Which is 2. 23. 23 mod 7. Well, 21 is a multiple of 7, so we're 2 over that. So our hash value, the desired index is 2. We want to put a 23 here, but we can't. So we look for the next available space, which is taken. So we look for the next available space, which is here. So we put in our 23. Next, 3. 3 mod 7 is pretty easy, right? If the mod is bigger, if you have x mod y and y is bigger than x, then you just have x as your answer. So we want to put 3 at index 3. But we can't because people got greedy and took my spot. So I look for the next available spot, but that's taken. So I'm going to take index 5, which, surprise, surprise, 5 is the next thing to insert. Can't do that there, so 5 has to go over here. Quadratic probing would act similarly for the first steps. 15 and 17 would go into the respective places. Now let's look at 8. 8 wants to go into index 1. It can't, so it looks 1 squared away. So it goes into here. Next is 23. 23 wants to go into index 2, but it can't. So it looks 1 squared away, but it can't. So it looks 2 squared away from the initial. So that would go, so it can't go into index 8. So looks 1 squared away, then 2 squared away, which is 2, 3, 4. So it looks over here. Second. Yep, 4 away from the original one. So it looks over here and goes, aha, there's an empty space. So I'm going to take it. 3 tries to go into here, but it can't. And then 5, gets plopped right into where it needs to go. So you get a bit less in the way of madness of having to do these things. So I'd ask you a question like part A on the final exam. Part C is something we didn't do, which is just simply, hey, if you've got a conflict, resolve using double hashing. In other words, if your first hash function doesn't work, try the other hash function. All right. I'm going to take a slight break to just the slightest break to go and get some water. And then I'm going to go and we're going to talk about graph algorithms. Okay. So about 5 minutes. I think I heard my kid up, but I don't hear him now. So just want to make sure everything's, hunky-dory. Okay. So it is, sorry about that. Just want to make sure, but everything was good downstairs. So depth first traversal of the graph shown above. Starting at vertex C. I do this graph all the time, but I hate it. It uses big numbers. Okay, depth first traversal of vertex C. Sorry, depth first traversal starting at C. Select the smallest edge visited when appropriate. In the space below, list the vertices in the order in which they are visited. So if we're starting at C, we need to choose a path to go down. So that means 5. So that means either B, E, or F. So we're going to go down. So we can choose any of them, but it says to break the ties by using the smallest edge. So that means we're going to go C to B. So our stack is C, B. Okay, and now we go down. Now we're at B. So now we choose the smallest edge where appropriate. We've been to C, so we can't choose that edge. 18, 20, 13. So we're going to choose A as our next one. Okay, next, A has 2 possible edges, but one of which has already been taken. We visited, so we go to D. And then D is at a dead end, so we pop off the stack to go back to A. So now we're at A again. Pop off the stack to go to B. B says we've got 4 possible edges. We've got 5 possible ways to go, but we've chosen 3 of them. So next we're going to go down to F because of the 2 possible edges. We've got 15. We've got 20 and 18. So go to F.
Why wouldn't you go to 17 for that smaller?
Because
Or
we've
to
already
D,
been to
rather.
B.
Oh, even though you popped it off, that still counts as
Yep.
visiting it.
That's
Okay.
why I circled them. Anything that's been visited in the visited list, we don't revisit because that'd just be retracing our steps and getting and going to places we've already seen. It's gone to F, go back to B, and then we go down to E as our final one. And then E is a dead end. So we pop off the stack, then pop off the stack, and then we pop off the stack, and we're done. So C bad FE is it. So now the next question is breadth first search, which I'm just gonna not bother moving the page. I'm just gonna clear this answer and do it. So for breadth first search, we need the queue of things, which we're gonna, since we're starting at C, we're gonna put C in our queue. And we've got our visited. Yep. Which is going to be our output. So I'm just going to put V for visited. And then S for our seen nodes. Which honestly is kind of unnecessary if you're doing it on paper, because if it's been seen, it's either going to be in the queue or the visited. Make sense? And our eyes can kind of tell that for us. So we're done with the queue. So we dequeue, put C into visited because we're there now. And now we want to add all of C's neighbors to the queue. So, and we'll go ahead and add them in the order in which they're the cheapest, which is 5, 22, and 30. Because that's still the way we break ties. B, E, F. I personally prefer doing stuff, which, I mean, this was equivalent to it, but I prefer to do stuff by breaking ties alphabetically if I need to. Just much easier to it's much quicker to process. Okay, B, E, F. So next we go and visit B, and then we would add all of B's neighbors to the queue. B has already had C, F, and E already added. So we've got A and D as our neighbors. So we would add A and D. And then all that's left is to actually just DQ our Q. So we do E, it has no neighbors to go to, then F, and then A, and then D. Because, so right, and we can kind of confirm this is a correct answer by we visited all the neighbors 0 away, which was C, then all the neighbors 1 away, and then all the neighbors that were 2 away. Okay, next question is Dijkstra's algorithm to find the shortest path from D to E. So we want to find the shortest path for using Dijkstra's going from D to E. So we're just going to start at D. So that means that we need to draw ourselves our, I'm going to draw myself a matrix, which basically has the nodes A, B, C, D, and E. Oops. C, D, E, F. There's our nodes. And now we will need the distance to each of these guys and the predecessor to each of those. So. And we initialize it by saying, hey, the distance from D to anything else is infinity. Make sense? So, and typically we would initialize it by also putting in, instead of infinity, things that D has a connection to. So we'll do that. D has a connection to A and B. So you could get from D to A for a cost of 13, sorry, for cost of 10, where from D. And you can get to B from a cost of 17 through D. All right, so and honestly, this one's a poor one for Dijkstra's because you don't do too much in the way of replacement. But again, the algorithm is as follows. So we're done with D. So let's go ahead and check. Let's look at everything that we aren't done with and select the one with the shortest distance. And that is 10 because 10 is smaller than 17 and infinity. So 10 was our smallest distance. That corresponds with A. So we're going to go A next. Does A give us have any edges we haven't seen yet? A does have an edge to our unvisited kind of area. So it's got 13. And so we ask ourselves, does 10 plus 13, which is the cost to get from A, sorry, get the cost to get to A plus the cost to get to wherever we're trying to go now. So 10 plus 13, is that cheaper than the cost we already know to get to B? No, it is not cheaper because that's 23. So we don't update that cost. So we're done with A now. So 17, infinity, 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 17 wins. So now we're at B. B says, hey, so what goes to new things? Well, 5, C and 5 does, 20 and 18 do. So those all go to. So let's look at C. The cost to get to B is 17. The cost to get to C is 5. So 5 plus 17, that's 22. Is that smaller than infinity? Yes, last I checked. So we'll put down 22. And we say we get there from B. Next, E would be 17 plus 20. So it's 37 from B. And then finally, we have 18 to F. We have 18 to F. So 18 plus 17 is 35. And we would get there from B. So now we choose the next cheapest thing, which would be 22, which is C. So can we get C has 2 additional nodes. So let's take a look. the cost to get to C is 22. 22 plus 30 is to get to F. That's lower or more expensive. The cost to get from C to E is 22 plus 22, which is again more expensive. And then this one just resolves by going to F next. Oh, there's nothing there, and then going to E. So there's only like, you only ever update the infinity, so that's why I say this one's not that great for Dijkstra's in terms of showing how it works. But yeah. If on the other hand, we were to change this and say, hey, this was instead of being, if this instead was 30 was 10 over here, here's what happened. We would say 5. Okay, so C to F is 22 plus 10. That would be 32. So we, in that case, we would update 32 at that point and say we could get to F with the cost of 32 by going through C. And then the question is, okay, so how do we get to C? Well, you get there through 22, sorry, through B. Sorry, you get there through C, which costs 22 going from B. You get to B by going to D, and D is our start location. So this contains all the information you need on how to get for getting to and from places. This is Prim's algorithm and minimum spanning trees. I did not cover those. Again, just time constraints as well. It's a matter of like what gets covered in which class. I'm pretty sure it does get covered in algorithms. You'll see in the exams that there's some, and some of this other stuff would get covered in data structures as well. Sorry, in object-oriented programming in other schools. So, all right. So let's go ahead and see the coding stuff. So this Java method uses recursion to search for the key of a binary search tree. Okay. So what they do is that they have their set up like a hash, their tree set up like a tree map, right? Tree maps are basically the only trees you have in Java. They're built in, or rather like the only kind of tree data structure that we use or resembles what we use. So, and what it does is that it uses a balanced binary search tree to do map operations. So the node contains both a key and a value, and it's sorted by the key. So benefit of using a tree map over a hash map is, while the tree map does everything in log n time versus the constant time of a hash map, you can basically make sure that things are because it's a tree, things will be sorted, and so you can iterate through it in a sorted manner, or you can just kind of directly output it in a sorted manner. And you can also do things like, hey, well, actually, it's just test. But basically, it gets rid of that whole constraint that we don't care about the order, and orders in hash tables are meaningless. Okay. So the following Java method uses a recursion to search for a key in the binary search tree. So this is like our standard binary search tree, right? If we're looking for an item in the tree, right? If it doesn't exist, we can't find it, return null. Otherwise, if the key is what we're looking, if we have the key of what we're looking for, return the data, right? This is similar to contains, except here we're using a key value storage, right? And then otherwise, if it's to the left, go search the left tree. Otherwise, if it's the right, go search the right. In the space below, rewrite the search method so it uses iteration instead of recursion, because we are gluttons for punishment. Okay. Basically, what we're going to do is, so basically it's saying write this without using recursion. Not too bad. So what I'm going to say is, hey, first off, if a root, the root we're getting passed in is equal to null, return null. Okay, that takes care of that. The base case there. What if we've got that takes care of any kind of null pointer exceptions we have. So what we're going to do now is and then I'm going to actually put a return null right here in case this fails. Okay. Actually, yeah, we don't need this at all with the way I'm planning on programming it. Okay. So what I'm going to do, because I don't know how malleable that root is, I'm going to just simply say node current is equal to root while current is not equal to null. So in other words, as long as we don't hit a null. So in other words, if we ever hit a null, we're just going to break out this loop and return null. So and now we just put in the if else statement, just we do it a bit differently, or the if else block. If current dot data, current dot key equals are the key that we are looking for, return current dot data, because we're returning, it's the key value kind of retrieval. And that's kind of the obvious part. And then the other part we need is else if current, what if the key is less than, because our key is an integer, so we can just do it like that, current dot key. Otherwise we'd be using a compare to, and that changes very little, just changes the conditions slightly. Else if current dot key is left, so in other words, we need to go to the right left subtree, we just simply say current is equal to current dot left else current equals current dot right. So it's a bit messier, but that's primarily because I did it with my handwriting rather than the computer itself, rather than doing it in IntelliJ, which I'll boot up now. So, but that's how you would do it iteratively. Okay. Clear all my drawings. Close. New project. Okay. New Java class. Class is okay. Now let's go and see what doom awaits me here. All right. Yeah, I like this one. This one's great. Totally would put this on the exam if it wasn't a practice question already. So write a Java method called mirror, which takes in a root node of a binary search tree and then creates a new node with its own nodes that is the mirror image of the original tree. So for example, if root is a reference to the tree to the left, so in other words, if we're given this root node then the returned value would be this root node, which has this as a subtree, right? See how everything is flipped in every possible way? 2 is flipped with 3, 3 is flipped with, and 4 is flipped with 5, but also the structure of the tree is also flipped. Looks like a bit of a doozy, right? I mean, it gives you that hint. This method is much easier if you use it using recursion, which it is, because it's really not that hard once you get your head around it and have done it like 7 times like I have. So let's go ahead and create ourselves our private class. Node E. Don't really care about doing our comparisons here at the moment. So what we're going to do is just simply saying, hey, private static class node E. And what we're going to do is that it will have an E item. I'm not going to do the object, like the key value thing. We don't need it here because what we have, all we care about is the node E left, node E right, and then we need a constructor, which will just simply be node E item. This dot item is equal to the item that I just gave it. Add a public in front because that's what I'm supposed to do, even though it's in the private class. But regardless, now let's go ahead and do public static E mirror public static E node E mirror, which takes in a node E root node, return null, or actually return node. Yeah, return null for right now. All right, base case time. So let's figure out what our base case for this is. So if root is equal to null is always a good thing to, right? Just for if no other reason to prevent nulls, pointer exceptions, or to mitigate them if possible. If root is null, what do we want to do? Well, what is the mirror image of if you shine a mirror to nothing, what gets reflected back? And the answer is nothing. So makes sense that the mirror image of nothing would be nothing. Okay. Otherwise, if we've got otherwise we have something. So node output, node E this isn't done yet, but I'm just simply, the idea here is that if I don't, so what do I need to do? If I've got myself a node over here, then I've got myself my left subtree, I've got myself my left subtree and my right subtree, then my output for this algorithm is going to be the same node at the top, but what's going to change is my left subtree and my right subtree. R and L. And furthermore, those things should have mirror called on them as well. Make sense? So what we're going to do, so this leads us to a pretty straightforward answer. It just, again, recursion seems like magic when you actually implement it, which is mirror root dot left. Its left side is going to be equal to the mirror of root dot right, and the mirror root dot right is going to be equal to our left, but after we apply mirror to it. I know that seems crazy that this is all that's needed for that problem, but that is all that's needed for that problem. Because what's going on here, we create a clone, just like we're supposed to, of our root, and then we say our left subtree is the right subtree, but passed into this function, which means that by passing it to this function, it's going to swap the right side's left children and right children around. And then that's going to do it for its own children and its own children, which is exactly what happens here. What is the running time of your implementation of mirror? Use big O notation. Well, since every single node gets passed into this and we create a copy of every node and then it applies to all of its children, which means this goes on to everything. This algorithm touches every node exactly once, so it's going to take O of n time. All right, we're touching every node, so it's going to take O of n time. So that's that practice exam. All right, so let's take a look at at some questions from this other practice exam over here. All right, so in their data structures course, they say they've gone through a lot of the same stuff we have. Lists, two-dimensional or higher arrays, stacks, queues, hash tables, trees, binary search trees, undirected graphs, directed graphs, and directed acyclic graphs, which, if you remember, directed acyclic graph means a graph with no cycles. That's what acyclic means, no cycles. And directed means, each node has a direction to it. Each edge is one way. And directed acyclic graphs are what's used in your last homework. Okay. So for each of the applications, indicate which data structure would be the most suitable and give a brief justification of your choice. Okay. So A, map of the Puget Sound highway system used to display traffic times on a web page. Okay. So it displays the principal cities, intersections, and major landmarks, the roads that connect them, and the travel times between the roads. Travel times along the same road may be different in different directions. So what is the appropriate data structure for this application? Anyone?
Directed graph.
Yep, it's a directed graph because and actually map applications like this are kind of the classic one where we're just basically creating because every destination you need to get to is the vertice. So your principal cities, landmarks, intersections, the roads that connect them are the edges. And then the travel time between them are the weights. And it's directed because, of course, traffic can always be different in different directions. Right? Chessboard, an 8x8 board used for a game of chess. Each square on the board is empty or contains a chess piece. We've done that one. That's a 2D array. Right? So a computer model showing the dependencies between the steps. You need to assemble a 787 at Boeing's Everett plant. So this one is a directed acyclic graph because dependencies are all, because directed acyclic graphs are all about dependencies, as you'll see in your final homework. They're all about basically what do you need to solve first, what leads to what. A list of legal words in a grapple game. We want to be able to quickly check whether the words used by a player do in fact exist in the list. I mean, it's using the term list, so array list maybe, but honestly, if you want to make sure you're really quick, use a hash set. Inheritance relationships, that's a tree. History of recording sites using by the user of a web browser. As new sites are visited, they are added to, there's the key word again, a list. So it supports operations going back to the web page that was previously visited before the current page, as well as going forward to the next page visited. In other words, these arrows on my web browser wants to implement them. Now, if we just had a back button and not a forward button, it would be a stack. But in this case, because we want to go backwards and forwards, we'd either need 2 stacks or a linked list. Okay. So let's see. Nodes in an integer binary tree can be represented blah, blah, blah. Complete the definition of a breadth first search to perform a breadth first search traversal of the binary tree and print out the node values in order they are reached during the search. You can use whatever other Dijkstra you want. So this is saying, hey, here's a tree. I want you to do level order traversal on it. I want you to do breadth first search. That's not too bad. Man, lecturing for hours is kind of a bit draining this early in the morning. Don't really. Oh, I much prefer doing it later. All right, but BFS, there we go. And we aren't going to return anything because we're going to just print everything out. Okay, so we need to do a breadth first search. Breadth first search doesn't really work recursively. Instead, it uses a queue, right? So, and we don't, but because we're in a tree and we're guaranteed to not have any loop backs or anything, the node, our edges are only one way. We don't really need to keep track of the nodes we visited. We just need to print out nodes in the order we encounter them, and the order that we're going to go through them is via their queue. QE is equal to QEQ is equal to new. And then you can't make a queue because it's an interface. So we're just going to call it a linked list. So we're just going to make a linked list and call it a queue and be done with it. Okay. Now Q dot offer the root. That's how we enqueue an item in Java syntax. There we go. Oh, queue of node E, my bad. There we go. So we've added it to the queue. Wow. Not queue dot empty. Well, it's not is empty. Well, we don't have a queue. What are we going to do? Well, we need to get node E current is equal to the current space we're on. That's going to be Q dot, and the DQ is polling. So we remove that from the queue. And then what we do is that basically we will sout our current just to simply say we traversed it through it. And then we need to go ahead and visit. We need to add our neighbors or our children to what we're going to be going through later. So if current dot right is not equal to null. So if I have a right, right going to be going right and left. So whatever, can just copy paste. Should do the left first. If left is not equal to null, it's very important that they're not else if statements because that would only ever add one child. So if you've got a left child, Q dot offer current dot left. And then if we have a right child, q.off or current.right. So in other words, if we print out ourselves, then add our left child and our right child to the queue, and then we just keep going through the queue again. So not too bad there, right? Okay, next item. Okay, there we go. Here's an adjacency list. There are no weights to the edges. This is a directed graph. So draw a picture of the directed graph that has the adjacency list representation. Okay, drawing this graph. So we want to draw the graph that is represented by this. So we got ourselves 4 nodes, it looks like. Well, 4 nodes. So yeah, let's go over here. A, and A is connected to B, C, and D. Okay. B is connected to A. This doesn't mean that A is connected to B, it's connected to C, it's connected to D. This is saying the key A has these as values. That's why I prefer to do it in a map. It makes much more sense to do it that way rather than a list of lists. So A has B, C, and D. B has A, C goes to B, and C goes to D. And D doesn't go anywhere because it's lonely or something, I guess. Dead end. Okay, next. Another way to represent the graphs is adjacency matrix. Make the adjacency matrix for this graph. A, B, C, D. A, B, C, D. Feel like I'm on an episode of Sesame Street now. A lot of that in my house lately. Sesame Street, I mean. Okay. So here we don't have any self-referential edges. So I'm just going to use 0 for there being no edge and 1 being the presence of an edge. We know that D doesn't have any edges there. So A goes to B, C, and D. B goes to A, but nobody else. C goes to only B and D, and B and D doesn't go anywhere else. So that's our edges. We could easily use true or falses. If we were trying to do this in a weighted manner, what we would do is that we would basically put these guys as 1.0s so that we could use doubles. And then if you're using doubles, you can actually use infinity as a value. So, and say basically you can get from, and basically if there's node, you can get from B to from B to D, but it's going to cost you infinite dollars to do so. Okay, so here we go. Dijkstra's algorithm on this guy is actually really good. Good question there, because it's an unwritten law of computer science education that if you learn about Dijkstra's, you'll see Dijkstra's on your exam. And if you're dealing with graphs, you're going to learn about Dijkstra's. Doesn't matter how many times you've learned Dijkstra's before. Okay, like I've done Dijkstra. I've had Dijkstra's algorithm on an exam. I think maybe 3 or 4 times during my curriculum, because nobody assumes that you got it right the first time. Okay. So Dijkstra's algorithm, starting with okay, this is annoying. So I'm going to relabel these things because this is one of the things that I just do not like, which is that if you're using weights, don't use numbers as your vertices, because that just gets confusing. A, B, C, D, E, F. So does that make sense why I'm relabeling it? Because I like to keep my data type separate. Okay. So first off, we're going to start with A, and our initial distances to everything is infinite, and we don't know how to get there. So let's go ahead and look at A and see what it has to what information we do have. A to B has a cost of 2. Get there from A. A to D has a cost of 3. We can get there from A. Okay, so A is done. So next we need to see which of these is the cheapest to get to. And so we've got B, we've got 2, infinity, 3, infinity, infinity. 2 is the smallest, last I checked. So we're going to go and look at B next. Now I like this one because this is actually a directed acyclic graph, by the way, which means that basically you start, and also if you start at any location, you're always going to end up in F. But anyway, B is our next node. And so let's take a look. Does B offer any additional information? So B to E is 3. So the total cost to get to E is 5 because it costs 2 to get to B. So so is the cost that it takes to get to B plus the cost to get to E cheaper than what we know for E? And so it's cheaper than, so 5 is cheaper than infinity. So we're going to go that way. Five is cheaper than infinity. So we're going to go B. Next, we have we have infinity, 3, 5, infinity. So we're going to go with D next. So let's see. D to C is 1 plus 3, that is 4. Is 4 cheaper than what we know? Oh, right. And I forgot to do this for C. Forgot to add this. Let's rewind back to B. B is 5 plus 2. Costs 7 to get to there. Okay, so back to D. D has 1 edge going out of it. D to C with the cost of 1. Okay, D to C has a cost of 1. So, so is 1 plus 3 cheaper than C? Yes, it is. 4 is cheaper than 7. Now we're done with D. So we've got 4, 5, and infinity. 4 is our cheapest one. Let's go ahead and do this one. It costs, so the only edge we have outgoing from C is 2 to F. So it's 2 plus the cost it takes to get this to C. The cost it takes to C to get to C, it's 4. Is 2 plus 4 less infinity? Yes, it is. 6 is less than infinity. So we put 6 down here. We get there from C. Okay. And now we're done with C. So now we have E and F. E is the cheaper one. And so we say, hey, it costs 5 to get to E, takes 4 more to get to F. 5 plus 4 is 9, less than 6. No, it is not. So we are done with E, and F has nowhere to go. So we're done. List them in the order in which they are processed by the algorithm. Well, I don't have the memory of a goldfish, so it would be A, B, and then we did E next. Then we did D, and then we did C, and then finally we did. Actually, we didn't do E. We did A, B, and then we did D. So we did A, B, D, and then we went to E. No, we did C first. C, E, F. Okay, so my memory is about as bad as a goldfish. Never mind. Okay, anyway. if V is the number of vertices in a directed graph and E is the number of edges, what is the running time of Dijkstra's algorithm in big O notation? So let's see. Any answers to that one? Because Dijkstra's notation really does depend on the big thing about it is you should also briefly describe any assumption you are making for the implementation that would briefly affect your answer. Because one of the things we have to do over here is basically so what are we going to do in this? Well, we have to, so what are we doing throughout this? Is that for every vertice, what do we do? So first off, we have to process this over here, this entire thing, this entire list over here, right? And what does that mean? Well, that means that basically that as we were going through it, we had to go through V. Basically, we checked each of the vertices, right? And each of the vertices, we basically said, okay, let's go and we have to figure out which is the cheapest among V vertices, then V minus 1, then V minus 2. So that converges to V squared, right? So it takes OV and OV squared time. Now, what about the edges? Well, each of these V vertices, we use a portion of the edges. Well, what's the worst case scenario? How many possible edges are there? Well, the worst case scenario is that everything has a direction to everything else, which is V squared. So the worst case scenario is, that basically it's V squared time, I believe, for this. But let's go ahead and see what Wikipedia has to say. Now that's assuming we don't do anything smart, by the way. If we don't do anything smart, then let's see. Runtime. Yep. So for a naive solution, so the upper bound can simplify it for any graph, but this simplification disregards the fact that some bounds, other upper bounds on E may hold. So if the graph is stored, so if we're doing an adjacency list, then V squared log V. Let's see. It's okay. But worst case of performance we'll see is it says is E plus V log V. Okay. Yep. So goes over here. While the original algorithm uses a min priority and runs let's see, it can also be implemented in big theta V squared using an array, which is what I just kind of described over here. What is the difference between big theta and big O, by the way? Because that annoys the heck out of mathematicians. Big O means worst possible case. Basically, it's bounded. You're never going to be able to be worse than this. Big theta means you're never going to be any worse, nor are you going to be any better than something V squared. But notice that it says, hey, if it uses a min priority queue. So if you use a priority queue, then the time actually gets reduced. And then the best algorithm, which was made in 1984, uses a Fibonacci heap min priority queue to optimize the running time to E plus V log V, which is kind of crazy. What the heck is a Fibonacci heap? Just go ahead and kind of look at it and visit it and let your eyes glaze over because it's insane, and then decide that you're just glad that you don't have to actually implement it. Okay. annotations. Clear. So, right. So two of the most common divide and conquer sorting algorithms are quicksort and merge sort. In practice, quicksort is most often used for sorting data in main storage rather than merge sort. Give a reason that it is preferred, that is the preferred sorting algorithm for application. So quicksort versus merge sort. So when it's saying main storage, what are they referring to? Are they referring to RAM or are they referring to? Yep, RAM, they're referring to RAM. So if you're performing it in RAM, in other words, if you're performing it on an array that you just created rather than on files types that are stored on your computer, it is preferred to do this way. If on the computer, you kind of prefer merge sort because merge sort, actually any sorting algorithm can be done via a map reduce process. So you can just simply like distribute that workload, but it's a completely distributed process. You can sort one side of it, then you can sort one portion, another portion, and you can merge them together. And in practice, quicksort is often more used than merge sort. So why? Why? Okay. So what's the disadvantage of merge sort? Merge sort always has two primary disadvantages. One, if you're doing merge sort on anything but a linked list, doing it in place is kind of insane. You have to use that extra memory. So merge sort uses all this extra memory that you don't want to have to handle. Where it has all this extra auxiliary memory, whereas quicksort can be done in place. That's one reason I would say. Another reason is that quicksort could have some optimizations built into it to help it possibly run a bit faster, whereas you're always merge sort, the way it's written, always does the same thing no matter what. Okay, now it says, now let's talk about what's actually implemented in Java, by the way. So let me go ahead. Collections sort. Java. Let's go to Java SE. Let's go to 11. I don't know why it always brings me to 7. Which is the current long-term release. So, and if we go and Control F sort, we notice that basically that sort does natural ordering. The sort is guaranteed to be stable. It says, why isn't it telling me what to do or what it does? You know, it tells me what it does, but it's not telling me what it uses. All right, well, let's take a look at, oh, right, sorry. Arrays sort. This will help us figure it out a bit better. There we go. The documentation of this method includes breach descriptions. Implementers are free to substitute other. For example, sort object does not have to meet merge sort, but it does have to be stable. So sort. So like parallel sort. Sorts it into ascending is a parallel sort merge algorithm. So arrays.sort. So Implementation note. This sorting algorithm is the dual pivot quicksort by Vladimir Yarovsky. It offers n log n performance on many data's that cause other quicksorts to degrade to quadratic performance and is typically faster than the traditional one pivot implementation. Okay, cool. Didn't know there was a two. Well, I knew because I've looked at this before, but this uses a version of quicksort that's so it does quicksort here. But now if I go and sort other things, if I sort objects instead, so if you're sorting primitives in Java, it's going to use quicksort. But over here, we notice that basically that implementation, this uses a stable adaptive iterative merge sort that requires far fewer n log n comparisons when the array is initially sorted. It is adapted from Tim Peters' list sort for Python, timsort. So it uses timsort over here, which is a optimization of merge sort if you're sorting objects. Why? Because it guarantees stability. Where basically, again, it's the whole thing of like if you get where basically two things that are the same value that appear, if you have two things of the same value, so if like you have a 5 of diamonds and then a 5 of hearts, then your output is guaranteed to be a 5 of diamonds, then a 5 of hearts, not a 5 of hearts, then a 5 of diamonds. That's what it means to be stable. But so anything that you're doing with objects will be sorted with timsort. Okay, so let's go. So now that you know about this, let's go back to here. What is the worst case? So quicksort's worst case running time, but as expected case n log n if the partition works well. What needs to be true about the function or for it to be n log n? For it to be, so what has to be true for a quicksort to be n log n? That the pivot basically has to split each pivot has to roughly split your array or subarray into equal halves. Right? So if you keep splitting it in half, you get the whole logarithmic time, which is what's going to result in n log n. In practice, how do you ensure that happens? By cheating and trying to find yourself a median, essentially. So one way we learn in the textbook is basically choose a small selection of numbers from the subarray and grab the median from that small selection. So at the very least, you can have some numbers that are smaller. Okay. All right. I think last problem before we go on. Last problem before we take a break and actually get and I give you the chance to work again. Okay. So because I also need, because apparently I need to hydrate my throat anyway. So insertion sort and merge sort for each algorithm. What is the worst? What will be the worst case upper asymptotic upper bound for on each runtime? So what is the big O? If you know additionally about these new additional facts. So insertion sort. So we're going to just look at these one at a time. Insertion sort. What's the worst case runtime if we know these facts? Insertion sort, I love insertion sort. It's my favorite algorithm because if it's already sorted, it's going to take O(n) time to sort because it will look at it and go, aha, don't have to push anything down. We're good to go. If it's reverse sorted, this is the worst case scenario for insertion sort. It will take O(n) squared always, and in like the worst kind of way. If it's just n copies of the same number, so it's size n, you have n copies of the same number, that's sorted. That's just a fancy way of saying it's already sorted. So also O(n). Merge sort, on the other hand, I would just simply say for each case, I would just simply write A, B, and C. All cases are n log n because merge sort don't care. merge sort works the same always, no matter what. It takes the same amount of time to do it, no matter what. That's why we like merge sort. It is consistent. It takes n log n no matter what. All right.
Why wouldn't it be constant time for C if every item in the list is the same? Couldn't it just always pick the first item?
Because it doesn't know that every item in there is constant. So it's going to split it up, right? Because it's never going to be constant time for either algorithm because it just doesn't know. At the very least, it's going to take O of n time to figure out that every item is in the same in there is the same, right? So again, and for merge sort, the reason it's still going to take n log n is because it doesn't know. It's going to just break it up into its little into individual pieces and start merging those pieces together, and the pieces take n log n, and it doesn't really care. It doesn't know. It doesn't care about what the values are until it actually has to compare the values. It just goes through it in a weird way. Now, the final note I want to make is that all the sorting algorithms we learned this semester, and I want to just expose you to this fact before we take a break. All the sorting algorithms we learned this semester are comparison-based sorts. And like we learned, for instance, like the worst case, the worst sorting algorithm to use is selection sort, because you do O of n, because for each space that you're trying to sort, you look at all the n items and put it in. So you have to do O of n comparisons for each of the n items, which takes n squared time no matter what. Now, this is a bit of an issue. This is a bit of an annoyance because, sorry, this is the reason it's the worst there is because it takes the most comparisons. Because we assume in most cases that the number of comparisons is the most time-consuming process or the most expensive process. However, if saying you're trying to sort a bunch of boulders by weight, right, you might say that lifting the boulder is much more expensive, in which case you care about the number of exchanges you have to make, the number of times you have to swap things around and move things, in which case selection sort is the go-to because you make the minimal number of swaps there. So sorting algorithms all depend on the context at which you're approaching them in, right? So just because something like merge sort is fancy and works in n log n time might not be the best resource for that problem at hand. Similarly, these are all comparison sorts. There are other sorting algorithms that don't work off, that can sort things without ever having to compare two numbers together. I normally go over this, but again, summer semester is abridged. Radix sort, I would normally give you a bigger explanation. The worst case performance of it is WN, where N is the number of keys and W is the key length. In other words, if we're sorting 10-digit numbers, if we're sorting n 10-digit numbers, the key W in this case is 10, if that makes sense. And what it does is that it was kind of a punch card sorting thing where basically you put you go from the least significant digit to the most significant digit. And so what you'll do is like, you say, okay, let me look at the ones place. And we're going to sort everything by the ones place. We're going to put all the zeros in one pile, all the ones in one pile, all the twos in another pile, and so on and so forth. And then I'm going to go and look at the tens place. So now we're going to put all the things that have a zero in the tens place, then a one in the tens place, then two in the tens place into these piles. And this will sort things by digits as we go up, without actually ever comparing two items to each other. It takes, as you can see, WN, and you're like, oh, well, W is smaller than N. Why don't we use this like all the time and everything? Well, in Java, in computers, we use integers, which are 32-bit numbers. So the size of the key, so then the key length here is 32. And so basically your numbers have to be, you have to be consistently sorting numbers that are bigger than 4 billion for this to make any, for this to make sense. It can get, so, but a lot of times we're just dealing with both big numbers and small numbers, so it doesn't really make sense to do that. But if you don't ever want to compare anything, then it's another cool way to do it.
For this, oh, sorry, go ahead.
Go ahead.
For this second exam you went over, I had a question about one of the first questions on it.
Sure. I'll be happy to go over that with you. Now that I'm done with my review session, I'm going to go and let me stop sharing and stop recording.